We are recording now. Okay, so you may have noticed that we are living that PowerPoint life. I've traditionally in the past kind of stayed away from PowerPoint as a lecturing style, but there were some reasons why I thought it might be good for these guys, or for you guys. Primarily because we're going to derive that final exam a lot from this content. I wanted to give you guys a little bit more of a concrete, like here's the stuff to study. Look at the slides, memorize the information on the slides. I have uploaded the slides as a PDF on Blackboard, so if you go up there, you can find them. And in like the back of the slides, like here, for example, let me just show you. Let me show you what I'm talking about. So all these slides are available for you. So I thought we'll see all this fun stuff. But also like in the back here, I like listed like here's all like the important like vocab stuff you need to work. Like these will like I don't know. I thought this would be a better way to give you guys something more concrete to have to study for the final exam. So let me know if you like this, if you hate this. But this is what we're gonna do. Like so, I thought this would be better moving forward. But you're right, Akil. The .pdfs don't have animated title slides. You just have to look at the static image. Whoa, 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 whoa. Hold on. That was not what we wanted. It just launched the slideshow on every screen. That was insane. Dang, it like nuked everything. Hold on. Sorry, I hit the wrong button in PowerPoint and it just nuked everything. It was terrifying. Don't hit that button. That button destroys the stream. Okay. I think everything's working. It's recording. It seems to be running. The stream is up. We can see the waves. Okay. So let's have class. So like I said, if you let me know what you think of this lecture, if it's a style you like and a sort of study method that you guys like, we'll keep using this going forward. Yeah. All right. So let's just go ahead and click our way through the magic. All right. So today's lecture is all about non-periodic signals, what we're going to call chirp signals moving forward. And there's really three main topics that we're going to hit today. One is what is a chirp signal? We're going to talk about spectrograms. And then we're going to talk about an interesting concept called spectrum leakage, which is an interesting byproduct of taking the Fourier transform of a non-periodic signal. So, chirp signals. By definition, a chirp signal is a signal whose frequency changes over time. It's a non-periodic signal. So basically, every signal in the universe is a chirp signal to some degree, right? Signals are very rarely actually periodic. Only, in RF communications, like a carrier signal would be periodic, but everything on the inside itself is not periodic. So a chirp is a signal whose frequency changes over time. And we call them chirps because when you play segments of them, they tend to sound like chirps, like little birds chirping, which is fun. So, but there you go, a signal whose frequency changes over time. Now we're going to consider two types of chirp signals today. The first one is a linear chirp. These are kind of perfect spheres in a vacuum kind of chirps. But a linear chirp is a signal whose frequency increases or decreases linearly with time. So we kind of ramp the frequency up or we ramp the frequency down, and we do it linearly. We're also going to think about what we call an exponential chirp, a signal whose frequency increases or decreases exponentially with time. So that makes sense. Yeah, so those are the chirps that we're going to look at in this class. But as we said, a chirp is any non-periodic signal. So an audio stream, such as what you're listening to right now, would be considered a chirp signal. It's just sort of a shorthand notation. So let's talk about implementing a linear chirp signal And as I was preparing for this lecture, I realized that we kind of started doing it wrong. We have that Think DSP, or we have the Think DSP book, and we also have that Think DSP class, or that Think DSP Python file. Now, it occurred to me that we, as I was reading in the textbook, we're actually supposed to be not using the Think DSP file directly, but we're supposed to be building it up as we go. And the idea is that what is in the Think DSP Python file is what we would end up with at the end of the book. So we kind of build it ourselves from scratch as we go and learn. So we're going to kind of start to do that, although we're still going to lean on that Think DSP file in this class for the rest of the semester. But next semester, I'll make them start building it from the ground up using the basic tools. But here, let's take a look at implementing that linear chirp. We're going to expand or extend on the signal class from Think DSP. We need to use NumPy to get some NumPy array business, and then of course we need matplotlib.pyplot to display our signal. We have our class definition here. Our chirp extends signal. We've got our constructor. In it, there's three major parameters: the start, which is the start frequency in hertz; the end frequency, so where we're going to start, where we're going to end. By default, we're going to use 440 to 880, which is just an A to a B in music, and a default amplitude of 1, and then we just assign those values in the constructor. Next up, there's a function that the signal class needs called evaluate, where we actually lay out the signal that we're going to put out there. And all this has here is frequencies, which is just a linear line space that starts at the beginning and ends at the end. So it starts at 440, ends at 880, and its length is the length of whatever the wave is that we're creating minus 1, so 1 less than the length of our signal. So this just lays out all of the frequencies, and then it passes it to a private function, evaluate, that takes TS and frequencies. So we're going to create an array of frequencies that is equal to 1 less than the length of the signal itself. And then the real magic happens here in this private method evaluate, which takes TS and frequencies. The first thing that happens is DTS, which lays out the length of each interval by calculating the difference between adjacent elements of TS, right? So the length and time of each different segment of our chirp signal gets calculated out. So this creates an array of those signals where each value in the array is the difference between it and the next array in time. dphi's is the change in frequency during each interval in time, so it's just 2pi times frequencies times time. So this is basically going to, you can think of this as setting the phase shift, right? Where is the signal at each point in time? And that's of course going to get shifted by the frequency that's shifting. That's really where the sort of magic happens. And then we have phases, or we essentially just take that and we add them all up because we want the signal to progress forward. Here's another example of an unfortunate NumPy name. As we move forward in our signal, we want to be pushing the signal forward. So we're always going to be incrementing the phase at each segment moving forward in the signal. So phase is an array containing where each element contains the cumulative sum of the dphi's array from 0 to that index. So we're pushing the signal forward at every space. And then just by accident, we need to add a 0 in the very beginning. So we're going to insert a beginning phase right there at the very beginning. And then finally, ys is where we calculate the signal. So we just multiply. We're going to create an array that is the amplitude, which we defaulted to 1, times, it's the cosine signal of each of those phases. So this is going to create our signal that's changing in frequency as we progress in time. So now let's go ahead and see what it looks like. If you haven't been doing this already, if you write a Python class, at the end of your file, after your class declaration, you can usually add some code to test your implementation, right? And it usually looks like this: if _ name equals main. Although I've read that this syntax, while it's like convention in the community, people do this all the time, it's actually not necessary at all anymore. Or at least it's not necessary in Python 3. But I still do it like a lot of people do it, just kind of out of habit. So all we're going to do here is just create a signal from our chirp class. We'll use all the defaults, so it's going to go from 440 to 880. and we're going to make it last for 0.05 seconds. So we just want to see a little bitty piece of that signal, and then we'll go ahead and plot it and show it. So there we go. So there's our chirp signal, and as you can see, it starts off in the beginning as a sort of wider sine wave, and as we continue in time, the frequency is sort of shrinking down until the very end here, when it is a higher frequency. So we're starting at 440, we're ending at 880. So you can see the waveform compressing as we move forward. Now I realize you guys might not be able to hear this. I'm going to play it anyway, but I included the audio file of the chirp. No, go back. I want to hear it. So, I don't know if you guys could hear that or not. Could you hear it? It goes whoop. Yeah, there we go. Play it again. Yeah. So we can hear that signal bouncing back and forward between 440 and 880. So, yeah, whoop. Does anyone have any questions about creating that linear chirp signal? Is the Fourier transform of this the derivative? No, I don't think so. Although it's ringing a bell in my mind, so I'm not going to commit to saying no definitively, but I don't think so. But we are about to take a look at the Fourier transform of it, though. The Fourier transform is pretty cool. Okay, so if there's no questions about the linear chirp, excuse me, let's take a look at your first programming exercise. All of these are in a PDF on Blackboard for you. That's due on Monday, or maybe we'll make it due on Wednesday. I'm not sure. And so the first one is pretty simple. We just did a linear chirp signal. So I want you guys to create a class called Expo Chirp, which extends the chirp class to produce an exponential chirp signal. And if you dig into the Think DSP textbook, or even in the Think DSP class, you'll find most of this. But I want you guys to take a look on your own and actually write your own code to implement the exponential chirp signal. Any questions about that? Like I said, you can find how to do this both in the textbook and in the Think DSP code file. All I ask is, so I expect you're going to look at it. So all I ask is, don't just copy and paste it. Actually type it out, just so you get some, you spend 5 minutes thinking about how it works. So don't just copy and paste the code. Go ahead and type it all out, even if you're just copying it from the book. So, but like I said, I recognize that it's in the book, and you can just use that. So, any questions about that? All right. So let's move forward, and let's say the spectrum of a chirp signal. What if we take the Fourier transform? What will happen? What will it look like? What does the spectrum of a non-periodic signal look like? Does anybody know? Does anyone want to wager a guess? It does look wacky, that's for sure. So let's see, we got wacky, a mess, the slope. So Akil is still holding on to the rate of change of the frequency. Or the impulses. And so I don't think it's going to be the impulses, because there's no individual sine waves, right? There's almost like an infinite number of sine waves. So if we go ahead and take here's the code to create the spectrum of the signal. We just take our chirp. We're going to start at 220 and go to 440. We're going to make a wave that's got a duration of 1 second, and then go and plot it. Let's see, rate of change of the frequency. No, Akil, I don't think it's that. Now you got me thinking. But no, I don't think it's that. The spectrum looks like this monster right here. So it's like this weird sort of like Tower of Sauron kind of looking thing, right? That's got, you can see it. So we started at 220 and we went to 440. So you can see that this first peak, you basically get a peak like where you started, and then you get a peak where you ended here at 440. And then you get this sort of like weird oscillation that's symmetric about the center point right here. So you get this weird like ball sort of signal in the middle. and kind of a sort of wavy horizontal line across. So yeah, so the spectrum of a chirp is a pretty wacky looking thing. But that's what it looks like. And the important things here are that it starts at where you started. So there's a big peak where you started, a big peak where you ended, and then some stuff in the middle. So here's a question. Could you say that there is a fundamental frequency here? So I showed you this and asked, what is the fundamental frequency of this signal? What would you say? Curtis says the lowest part. Some other folks are typing. The middle, the left edge. Yeah. Can there be two, highest and lowest? Maybe. No. So the same. This is still a spectrum, and the same sort of rules. This is why I'm taking the time to like include like vocabulary, like this was like a middle school class, right? Because it's important to note. Remember our definition of. So this is still a spectrum, and our definition of the fundamental frequency is the lowest frequency component. So yeah. So by definition, the fundamental frequency here would be the lowest. It's still the lowest frequency component, right? So it's still going to be this peak that is at 220 hertz. And then there's now a real question, and I'd have to go back and plot it, and we'd have to sort of measure to see is, well, which one is the dominant frequency? Is there a difference between the 220 and the 440? So that might be kind of tricky to see. So there's still peaks, right? So this is still a fundamental frequency. So we still have harmonics coming all the way down. Now the space between the harmonics gets shorter and shorter. We have this weird business that happens here. But yeah, so the important thing is don't let the weird shape of a spectrum sort of scare you away from the basic definitions, right? The fundamental frequency is still the lowest frequency peak, right? It's still going to be this 220. But here again, we can kind of see that it happens at 220 and it ends at 440. But again, if we did other kinds of chirps, it might not quite look the same as this. So maybe spend some time over the weekend if you care to sort of create some different types of chirp signals and kind of see if you can mess around with what this looks like. And now, but there's a limitation here, right? Which is you can tell where it started, you can tell where it finished, but it's all kind of soup in the middle, and you really can't tell how long the signal was, right? This was a signal that lasted for 1 second, but you can't tell that from looking at this, right? There's no time information here, right? And time information is important because we're dealing with a signal that is non-periodic, so we need to see what frequencies are happening at what time. This brings us to the spectrogram. So a spectrogram is, well, first off, here's the question that we're dealing with. When we plot the spectrum of a signal, we only see the total frequency energy. We cannot see the relationship between frequency and time in our chirp signal, right? When we look at the spectrum, all we've got is the sort of soup of the frequencies that occurred in the signal. And we can't really tell any other information. So when you're dealing with a non-periodic signal, a spectrum is really not the most useful tool, right? It's cool to look at, but it's really not going to get you anywhere useful. So we need a spectrogram in order to get that time information out. So you can think of a spectrogram as sort of like a two-dimensional spectrum, or three-dimensional spectrum, I guess you'd say. Now to calculate this, we use what's called the short time Fourier transform, the STFT. And by definition, it's a function which recovers the relationship between frequency and time by breaking the chirp signal into segments and finding the spectrum of each segment. So we essentially take the signal and we chop it up into pieces, and we're going to take the spectrum of each individual piece and we're going to lay them next to each other to create this like 2D kind of map of frequency versus time. So our official definition for a spectrogram is a plot which shows time on the x-axis and frequency on the y-axis. In each column of a spectrogram shows the spectrum of a segment using color or grayscale to represent amplitude. So that just means it's going to be a slice of the spectrum at each point in time. Think DSP makes it pretty easy for us to look at a spectrogram. It comes right off of the wave class. So wave.make spectrogram. Now we have to define a segment length of 512, and there's some consequences to choosing 512 as our spectrum length. And let's see. So yeah, 512 is chosen for the segment length since the Fourier transform, the FFT algorithm itself, works best when you have a number of samples that is a power of 2. So you want to choose something like, hold on, let's see. Edward asks, if we aren't in the time domain, do we need to interpolate it first to arrive at a spectrum? No, like I said, we're just going to think of it as taking segments. Like we're going to take little pieces. We're going to take here, we're going to take our signal, that 1 second chirp. We're going to chop it up into 512 pieces, and we're going to take the spectrum, we're going to pretend that each of those pieces was periodic, and we're going to take the FFT of each of those pieces individually. And then we're going to plot, here we define high as 700 because remember that if we go all the way back, our default signal, our default frame rate for our wave class is that 11,025 hertz signal, right? Which means that we would have up to 5,000 hertz, so 5 kilohertz would be our top line. That's our folding frequency. But our signal only goes from 2 to 400, so we do 700 just to kind of cap it off at a place. Oop, let me go back. And then, yeah, like I said, you want to choose a power of 2 for your segment length, and that just says we're going to chop up our signal into that many pieces. So you get a thing that looks like this, which is, I think, a pretty cool signal. So like I said, the horizontal axis is time. We're going from 0 to 1 seconds. And then the vertical axis is frequency. So we can see that we started right here at like 220 hertz. And we came up to that 440 hertz place. And we can see how the frequency changes over time. We already talked about this. The plot is cut off at 700 hertz. Since that frame rate is set at 11,025 hertz, the full spectrogram would extend to half of that distance. The spectrogram, just like the spectrum, cuts off at the folding frequency. It cuts off at the Nyquist frequency, which is 1/2 of the frame rate. So since we only care about 200 to 400 hertz, going all the way to 5,000 hertz would sort of give us a spectrogram that's not very interesting to look at. So we cut it off at 700. And notice the line is kind of blurry. This has to do with limitations in the time and frequency resolution of the spectrogram. So we have to choose when we choose that segment length, we're kind of going to set our time versus frequency resolution. And there's some important trade-offs that you make when you set that value. So let's look at that, time versus frequency resolution. The definitions here are pretty obvious. Time resolution is, in a spectrogram, the duration of the segments, which corresponds to the width of the cells in a spectrogram. So the time width, if we were to say, like, well, how much time does the width of each of these cubes, each of these cells represent? That's our time resolution. Frequency resolution is going to be the vertical size of our cube, right? And they're always going to be the same size. Since we set 512 as our segment size, we're going to get cubes that are vertically and horizontally the same size. Frequency resolution in a spectrogram, the frequency range between elements in a spectrogram, in the spectrum, which corresponds to the height of the cells in a spectrogram. Now, what are the time and frequency resolutions of our example here? So in the spectrogram example, we chose, each segment was chosen to be 512 frames. So 512 samples. The frame rate is set at 11,025 hertz. And the time resolution is equal to 512 frames divided by 11,025 frames per second. So it's frames divided by frames per second gets you seconds. So the time resolution here is 0.046 seconds. So each cell, the width of each cell, is 0.046 seconds. It's got a really simple formula. R sub t is equal to n over r, where n is equal to the number of frames, and r is equal to the frame rate. So by increasing the number of frames, you can increase the resolution of time, or you can sort of shrink down that resolution by increasing the frame rate. I see Akil keep typing and then stop typing and then start typing and then stop typing. I just want to know what your question is, Akil. The suspense is killing me. the spectrogram does. Let's go back and take a look at it. But not like directly, right? You still have to calculate the slope of this line in order to get the rate of change. So yeah, so you can look at this and you can figure out the rate of change, but it is not itself directly the rate of change. You would still have to take another calculation step, right? It gives you a line, and from line, you know, your high school Algebra 1 class taught you how to calculate the slope of a line. So you can get the rate of change pretty easily from this. But the calculation itself isn't directly the rate of change. The derivative of this line would be the rate of change. You were close though. That's pretty good. All right. Let me click back through all of these again. So there we go. Time resolution is number of frames divided by the frame rate. Let's talk about frequency resolution. In the same example, still had 512 frames, still had a frame rate of 11,025 hertz. The frequency resolution, though, is frames divided by, or excuse me, frames per second divided by frames. So 11,025 frames per second divided by 512 frames gets us a frequency resolution of 21.5 hertz. So if you go back and look at the spectrogram, the vertical size of each of those cells corresponds to 21.5 hertz. So you can sit there and count. Now, this means that R sub f is equal to R over N, which where N is the number of frames and R is the frame rate. So RF is the inverse of RT. So frequency resolution and time resolution are inversely proportional to each other. So what that means is there's a bit of a trade-off that happens. That trade-off has a name. It's called the Gabor limit for the mathematician that came up with it. And the Gabor limit is the trade-off between frequency resolution and time resolution when creating a spectrogram. So RT is equal to N over R, and RF is equal to R over N. This means that you have to, when you're creating a spectrogram, depending on your application, you have to make the decision what is more important to you. Do you need time? Is time resolution more important? Do you need a shorter time resolution because you're looking at signals that are, frequency that's changing really quickly? Or do you need to measure the amount of frequency that changes? Do you need more frequency resolution, right? And you're going to have to make a trade. If you want more frequency resolution, you got to sacrifice some time resolution. And if you want to get some time resolution, you got to sacrifice some frequency resolution. So that's called the Gabor limit. Basically just a trade-off between frequency and time resolution. So any questions about spectrograms or resolutions or any of that stuff? Anyone who is thinking about the capstone project should be very excited about spectrograms. Now a bunch of folks are typing. Let's see. I had a question and realized it was the answer to the capstone. What was the question, Nikhil? Maybe it's not. Maybe I'll answer it. Maybe it is, and maybe I'll answer it. Or is Akil saying he's already done the capstone and he doesn't want to spoil it? Also, that was like the most anticlimactic thing ever. There was like 4 people that all started typing at once, and then like they all one by one like gave up, and then it was just Akil left, and then he's just said he didn't have a question. As opposed to what, Edward? Edward says, so this strictly works when we're in the time domain. What other domain would we be in? Oh, that's okay. So let me specify. So we do have discrete signals, right? We set the frame rate, right? So the signals that we're working with are discrete signals. They're not continuous. So technically we are in the in domain. Correct. Yeah. So what happens is when you take the make wave function, right? Well, in both cases it's in the in domain, right? Since we're working with it on a computer, there is no continuous function. But we're in that place where, remember, once you did the conversion, we talked about this a couple weeks ago, or maybe like a month ago, where we're operating in a place where the continuous function and the discrete function are sort of so mathematically similar to each other that it isn't even worth taking the time to differentiate between the two. But yes, setting the frame rate does have consequences, like we saw last time with aliasing, and now we're about to see actually with our next topic, which is spectrum leakage. So spectrum leakage is a pretty cool thing. So the discrete Fourier transform always treats a wave as if it is periodic, right? By the way it works, you have to give it a periodic function, right? But that's almost always not the case. As we discussed, no signals in the real world are actually periodic, right? They all have some kind of noise, they all have some kinds of, they got stuff going on. Maybe there's signals that themselves are not periodic, or like I said, there's noise. There's almost never a really, truly periodic signal, right? Periodic signal is a mathematical construct. It's a perfect spheres in a vacuum sort of thing. And one of the major problems that you face is discontinuity at the beginning and end of a wave segment, right? So if we take what we just did to create our spectrogram, right, we chopped the signal up into pieces, right? Now for a periodic signal, if a signal was periodic and we chopped it up according to its period, the DFT expects for there to be essentially the values end and begin at the same place, right? If it starts at 0, it's going to end at 0. If it starts at 1, it's going to end at 1. But again, that doesn't always happen. And so these discontinuities at the beginning and ends of our segments cause problems. So let's take a look at what that looks like. First, let's consider an ideal sinusoid. So our code for creating an ideal sinusoid is, we're going to create a sine signal at 440 hertz, and we're going to make a waveform that is just 30 periods of that signal. And then we're going to take a look at the spectrum. So 440 hertz, we're going to look at 30 times the period and take a look at the spectrum. So here's our sine wave. Notice now, if you pay attention really carefully, you'll see that like the end kind of gets cut off. But for the sake of this discussion, you can say, yeah, it is. It starts at 0 and it basically ends at 0. It ends at almost 0, minus a little bit of cutoff. So we have a periodic signal, and when we take the spectrum of that signal, we get a really nice, clean-looking impulse function, right, at 440 hertz. Right, it's basically flat lines, and then it shoots up directly to the top there, and then comes back down. Right, there's really no confusion there. So that's for a pure sine wave signal. Now, what if we mess it up a little bit? We're going to take the same signal, 440 hertz sine wave, but this time, instead of making our segment 30 periods, we're going to make it 30.25 period. What will happen here is this will cause the sine wave to start at 0, but it's going to end at 1. We're going to create a huge discontinuity in our sine wave segment, which is going to cause some problems when we create our spectrum. So if we go and create the spectrum, or first off, let's create the signal. And here you can clearly see, right, on the left-hand side, you can see where the signal starts at 0, right there. And then at the end, you can see it ends at basically 1, right, minus a little bit of cutoff, but it's there at 1. There's a huge discontinuity between the beginning and the end of the signal, which is going to make the discrete Fourier transform very angry. and you're going to get a signal now that looks like this, where we have, instead of going like a flat line and then a jump up to 440 and then a jump down and then a flat line, we actually get this curve up, right? We have frequency content that exists on the edges here, right? We think of this as frequency energy leaking out of that 440 hertz impulse function. So that's why we call it spectrum leakage. Now, if we put both of these signals next to each other, you can see a little bit more clearly. You know, the one on the left-hand side was the pure sine wave, and the one on the right-hand side is the one with a discontinuity. And so you can see really the difference between the impulse functions. One is the left hand is a very clean impulse function, and the right one has this spectrum leakage off the sides. You know, if you were in lab 3 and you took if you looked at the sort of spectrum analyzer of, you know, a sine wave signal, yeah, Keel, we're going to come back to that exactly here in just a second, right? So if you've ever like looked at a physical sine wave on like a spectrum analyzer, like in your lab 3 class, it's going to look like this because, like we said, all real signals are not periodic, and so you always have some spectrum leakage on the edges of a signal. So yeah, as Akil asks, would filters solve this, or is that something else? Actually, no, we do use a filter to solve this, but it's not quite a filter. You can think of it as a time domain filter. And that's the thing. Here, I'll wait for Andres to finish typing if he has a question before we move on to this next bit. So now I feel like if I say your names, then you're committed to actually finishing your question. For the clean sine wave impulse, does it actually have a slope, or is that just being able to graph it? Oh, yeah, I see what you're saying. So it looks like, well, it's not a perfect up and down. That's just from graphing it, right? If you were to take a really close look at it, that's just like, it's a straight line. If we were to do a scatter plot instead of a line plot, we would see like dot, 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 and then one dot up at 440, and then dots all the way down. Whereas if we did the scatter plot of here, we would actually see the dots creeping up like that. So yeah, so this is the fact that you see a slope on this line is just a byproduct of how we visualized the signal. So a scatter plot actually would be a better option. Okay, so as Akil asked, would a filter solve this? And the answer is, yeah, kind of. But we're going to use a technique called windowing to do this. A window is a function designed to transform a non-periodic signal into something that can pass for periodic. It won't actually be periodic, but it'll be pretty darn close, and it will reduce that spectrum leakage as much as we can. So let's take a look at what that looks like. And we'll talk about windowing in a little bit more detail later on, but here we're just going to sort of introduce it as a concept. So imagine a non-periodic signal. Something looks like this, right? Starts at 0, ends at 1, right? Huge discontinuity. So, and this is non-periodic. You might be sort of tempted to look at this and say, well, this is obviously a periodic signal, but because of the discontinuity, our segment makes the signal non-periodic. Because if it ends and begins at a different place, then for the purposes of taking a Fourier transform, it is not a periodic signal. So a window function says, let's take this and let's multiply it by a signal that looks like this. This is a window function. Specifically, this is what's called a Hamming window. There are a bunch of different types of window functions, but this is one of the most popular. And so what this does is we're going to take this and multiply it on our segment. So we're going to have, it starts basically at 0 and goes almost to 0. And it's not hard to see what's going to happen here, right? When we multiply this by our signal, we're going to get something that looks like this, which is, again, not very periodic. All this, this one to your sort of instincts looks less periodic, but it satisfies that criteria of all of the frequency content is still there, but it's going to limit the discontinuities as much as we can, right? We went from here where we had huge discontinuity to here where we have just a little bit of discontinuity. Now, there's some trade-offs by the fact that we cut off all this other stuff. It has some consequences on its own, but it's still a better option than just having those massive discontinuities. So why wouldn't we just use a bandstop filter, is what Hunter asks. And the answer to that is because a bandstop filter works in the frequency domain, right? But remember, we have to, at the end of the day, stuff has to happen in the time domain. This is a time domain. You could think of this almost like a time domain bandpass filter. That's kind of a dangerous way to put it because it's not really that, but you could sort of think of it as that. We're going to put a filter in the same way that we would put a filter on a frequency domain thing to sort of filter out some stuff. This is like saying, let's put a filter on the time domain segment itself. So what this will do is, for each of our segments, we will attach a Hamming window to it, and we'll do that windowing on each of our segments. And so it'll force each of the ends of the segments to be as close to 0 as they can, so that each segment has its own little bitty piece. And it keeps the discrete Fourier transform happy. That's windowing. And like I said, we'll talk about windowing in more detail a little bit later on, but just as a concept, you need to be aware of it for now. So, any questions about windowing? All right. Let's talk about, that's actually it as far as the lecture. The next thing I want to talk about is the second programming exercise. And I think right now on Blackboard it's listed as due on Monday. I'm going to extend it to Wednesday for you guys because I want you to spend a little bit more time with this, and also I want you to, enjoy your weekend. On Blackboard, you will find a .wave file containing a text message encoded using Morse code. Write a Python script to plot the spectrogram of the signal, and then on your plot, I want you to, pull it out and put it in MS Paint or put it on your tablet or whatever you're using, and I want you to annotate your plot or, print it out and write on it with pen and scan it. But annotate your plot, and I want you to tell me what the fundamental frequency of the spectrum is, and I want you to identify the individual characters of the message. And then I want you to include both your .py script and your annotated plot image in your submission. So if you don't see the correlation between this and your capstone project, then you're just simply not paying attention. I want you to take a .wave file where I've encoded a message, but here, really, honestly, the only difference between this and your capstone project is I've told you ahead of time what the message is encoded as. So here the message is encoded as Morse code. So I want you to take this, import the waveform. So the capstone, I don't believe, is in Morse code. So you have to do there are some additional steps, but this is the biggest step towards your capstone project, right? Take a wave file, look at the spectrogram, and then use the spectrogram to make some observations about what's going on in the signal, right? Google Morse code and look at the spectrogram, and you should be able to see what the messages are and stuff like that. So, I see, yeah. I thought you might be leaning that way. So that's what I'm trying to do this. Like I said, your capstone project, the sort of spectrum or the message is encoded a little bit more sophisticatedly than simply in Morse code. But you can think of this as a warm-up for your capstone project, right? You need to take the waveform, because on your capstone project, you definitely need to take the waveform and look at the spectrogram. And looking at the spectrogram is going to give you a place to sort of jump off from to start exploring other options. But here, I'm telling you ahead of time, it's in Morse code. And honestly, if you were to look at the spectrogram, it's pretty obviously in Morse code. And then, so plot the spectrogram, print it out, or put it on your tablet, put it in MS Paint, scan it, and then annotate. I want you to circle. Here's where the fundamental frequency is. It's at X hertz, and I want you to, sort of circle all of the individual characters and write the letter next to it so you spell out the message. I want you to do that by hand. So, like I said, think of this as a warm up for your capstone project, where you're going to take a spectrogram and take a look at it. And there we go. All right, there we go. Look at that. We almost went full time too. That's pretty good. One of the reasons I stay away from PowerPoint lectures is I tend to go like way, way faster and end up finishing 20 minutes early, which I'm guessing you wouldn't think is a bad thing. But yeah, just to recap, we talked about chirp signals, we talked about spectrograms, and we talked about spectrum leakage. And your exercises are to create a exponential chirp function and plot the spectrogram of a Morse code signal that I've given to you on Blackboard. So, any questions about these exercises or anything that we've talked about today? My whole life I've always said that's a negatory Ghost Rider. And then I watched Top Gun like 2 weeks ago, and he said that's a negative Ghost Rider, and my heart was a little bit broken. All right. Well, if there's nothing else, then that is it for today. I'm going to hit stop on the record.